It's my pleasure to give a talk on this virtual workshop. So today my topic is on the escape rate of geodesic loops in an open manifold of non-negative Ricci curvature. So here is a new terminology, escape rate, that I'm gonna explain later. So this talk is mainly about the fundamental groups of open manifolds with non-negative Ricci curvature. So we'll start with the Cheeger-Gromoll splitting theorem, which is a fundamental theorem in non-negative Ricci curvature. It says that if you have an open manifold, non-negative Ricci curvature, if this M contains a line, then your manifold must split isometrically as R cross products on N. So here, a line just means an isometric embedding from R to N. So this splitting theorem has a corollary on the structural fundamental group. So if you have a closed manifold of non-negative Ricci curvature, then using the above splitting theorem, you can show that the fundamental group contains an abelian subgroup of finite index. Or we just say that pi1m is virtually abelian for convenience. I'm gonna talk about how this is proved later, but now we move on to open manifolds at this moment. So we're gonna talk about open manifolds of non-negative Ricci curvature. But for the sake of doing some comparison, we first record some results of open manifolds of non-negative sectional curvature. So this is fully characterized by the Cheeger-Gromoll saw theorem. It says that if you have an open manifold of non-negative sectional curvature, then M contains a closed, totally convex submanifold. In particular, this S is compact without boundary, so that M is diffeomorphic to the normal bundle over S. So as a corollary, you can see that M is homotopic to S. Then there's also the so-called Sharafdinov retraction, says you can construct a one Lipschitz retraction map from the entire manifold to its source S. So as corollaries of the above, so one can show that pi1m is virtually abelian. Well, this is because pi1m is the same as pi1s. And we know that S is a closed manifold of non-negative sectional curvature, which is virtually abelian. So pi1m is virtually abelian as well. And then secondly, if we fix a point inside the saw and we consider the fundamental group based at the point P, so pi1mp, then for any element inside this fundamental group, we can choose a loop based at a P of the minimal length. And this loop will be a geodesic loop, and we'll just call it a representing geodesic loop. So this corollary says one can always find such a representing geodesic loop containing inside S. Well, this is because if you have one minimal representing geodesic loop outside S, so let's say this is S, and you have one outside S, then you can apply this retraction that will map this C to, this is C, then F. Then this new loop will be contained inside S, and it's homotopic to C, and it also has length at most that of C. So it's, if C is a minimal one, then this new loop is still a minimal one, but contained in S now. All right. Okay, so now we move on to open manifolds of non-negative Ricci curvature. We'll see that it's quite distinct from the case of non-negative sectional curvature. We mentioned before that non-negative sectional curvature, you have this virtually abelian of fundamental group, while for Ricci curvature, non-negative Ricci curvature, it's possible that the fundamental group is not virtually abelian. This, the first example is constructed by Wei. She showed that any torsion-free nilpotent group can be realized as the fundamental group of some open manifold of positive Ricci curvature. Then based on this construction, later Wilkins showed that any finite generated virtually nilpotent group can be realized as the fundamental group of some open manifold of positive Ricci curvature. So on the second part, I mean here, the first part is virtually abelian. The second part is you can always find a representing geodesic loop inside, like at least a bounded set. But the second part is also it also fails from time to time for non-negative Ricci curvature. These representing geodesic loop may not be contained in any bounded sets of M. And in fact, Sommerly and Wei showed that if M has positive Ricci curvature and an infinite fundamental group, then this escape phenomenon always occurs. In other words, if you take the representing geodesic loops of all elements inside your fundamental group, then these loops cannot be contained in any bounded sets. They are escaped from these bounded sets. So another structure about the fundamental group of open manifolds with non-negative Ricci curvature is this result by Milno and Gromoll. So we have seen that virtually abelianness is not in general true, but it is true that they are always virtually nilpotent. So Milno showed that any finite generated subgroup of pi1 and p has at most polynomial growth. Then by a result by Gromoll, then such a finite generated subgroup will be virtually nilpotent. And we also mentioned that it's conjectured by Milno that the fundamental group should be finitely generated if the manifold has non-negative Ricci curvature. Later on, this result is generalized by Kopowicz-Wilkins. They show that the index can be bound, first of all, the index of the nilpotent subgroup. Then secondly, you can drop this finite generation condition. So more precisely, they show that pi1m always contains a nilpotent subgroup n of index at most Saint-Cyr constant. Moreover, any finite generated subgroup of this n has nilpotency length at most n. So we summarize all the above mentioned results in this table. So we have an open manifold of either non-negative sectional curvature or non-negative Ricci curvature. Then if we have non-negative sectional curvature, we know that pi1m is always finite generated and virtually abelian. Well, it's virtually abelian, then will also be virtually nilpotent as well. While for non-negative Ricci curvature, it's unknown whether the fundamental group is finite generated or not. And it may not be virtually abelian, but it's always virtually nilpotent. So then we can ask a natural question. So on what additional conditions is pi1m indeed virtually abelian for non-negative Ricci curvature? Well, surely you can also ask when, on what conditions is pi1m finitely generated, but that will be another topic, right? So in this talk, we mainly focus on the virtual abelianness of the fundamental group. So now we mentioned that there's an analog, this result below. We said it before that if we have non-negative Ricci curvature on a closed manifold, then pi1m is always virtually abelian. For open manifolds, and here open surely means non-compact and complete, there's an analog here. So if we fix a point, so here should be p, that's a typo. So if there is a point p inside M, so that all the representing geodesic loop in pi1mp is contained in a bounded set, say a ball of radius r, then pi1m is indeed virtually abelian. So I'm gonna mention how this is proved and also how the closed manifold case is proved. So we know. So let's first consider the closed case. So we have M closed. Then we're going to consider its universal covering. So applying the Cheeger-Gromoll splitting theorem to the universal cover, we know that one can show that the universal cover is always a metric product, Rk times some n, and this n is compact. So the fundamental group, we know that the fundamental group acts isometrically on the universal cover via path lifting. So in this way, we can view this gamma, so here gamma is the fundamental group, as a subgroup of the isometry group of M tilde. Here M tilde is the universal cover. And because M tilde has that splitting structure, Rk cross n, then its isometry group will split as well. So it'll split as isometry Rk cross isometry K. Sorry, isometry N. And this, the isometry group of N is compact because N is compact. Okay, so gamma here, we know gamma is virtually nilpotent. We can apply the result by Muno and Gromoll here. That actually simplify the proof because we can start with nilpotent groups. So then there's a result, there's an algebraic result, not very difficult to show actually. Actually, any nilpotent subgroup inside isometry Rk times a compact Lie group, then it must be virtually abelian, right? So then you can show that gamma is virtually abelian. So that's roughly the story. So when M is open, then the universal cover may not have this splitting structure as Rk times a compact thing. It could be Rk times a non-compact thing. But if there is a line, we can still split that. So let's say times n, but this n may not be compact. But if we assume that, well, because it's not compact in general, so we cannot view, say, gamma as a subgroup inside, say, isometry Rk times a compact group directly from the splitting structure. But if we assume the assumption here, that is, all the representing geodesic loop are inside VRP. So representing loops in VRP, sure that this means all representing geodesic loops. This will imply that this gamma, you can view it as a subgroup of isometry Rk times some K. So here K is a compact Lie group, although not the entire isometry group of N, but a subgroup of that. Then by a similar story, because this gamma is virtually nilpotent, then you can show that gamma is indeed virtually abelian. So that's roughly the story. On the other hand, we know that the assumption in this analog may not be true in general, right? So I think I made a mistake here. So here should be a Ricci curvature. I'm sorry about that. Here should be Ricci curvature. Okay. On the other hand, we know that for non-negative Ricci curvature, this assumption may not be true in general because due to the escape phenomena that we mentioned, these representing geodesic loops may escape from any bounded sets. So especially when you have positive Ricci curvature, then it will always escape from bounded sets. Then we cannot apply the above result. So we naturally ask a question here, how can we improve this result? Okay, before giving an answer on this, now we look at some motivating examples. These are open manifolds of positive Ricci curvature, actually. So the first class of examples are constructed by Bernard and Baudry. So let ng0, so we start with this ng0, which is a closed manifold of non-negative Ricci curvature. So Bernard considered the case this n is a circle, then Baudry generalized this to any closed manifold of non-negative Ricci curvature. So given such an n, one can construct a so-called double warped product. Its metric looks like this, so that it has positive Ricci curvature when P is sufficiently large. So here, H and F are the warping function that you need to choose in a nice way. So in their construction, so this HR, so HR is the warping function of this n. It either goes to 0, it's always decreasing, but it either goes to 0 or goes to some positive number C as R goes to infinity. And also in this example, well, M is diffeomorphic to, let me mention it here. M is diffeomorphic to RK times N. So the fundamental group of M is always the same as that of N. And the fundamental group of N is virtually abelian, so the one of M is also virtually abelian. So here is a picture when, say, N is a circle. So this is the circle vector here. So you can see that it's decreasing as R goes to infinity. So this is the R direction. Okay, so that's the first class of examples. The next one is the examples constructed by waves. So this is the first example, says that you may have a manifold of positive Ricci curvature and a fundamental group that is not virtually abelian. So it starts with a simply connected Newport Lie group, this N tilde, and then we choose a lattice inside that. Then N tilde modulo gamma, this N, this will be a compact one. This one is compact, and it admits a family of matrix GR. So here R is a parameter, non-negative parameter, with almost non-negative Ricci curvature. So N does not admit positive Ricci curvature, but it admits an almost non-negative one. So then for suitable function FR, so this is the warping function on the sphere, then this warp product indeed has positive Ricci curvature when P is sufficiently large. So this is not a double warp product in the usual sense, because this N sub R, the matrix here, it decays at different rates for different steps of that Newportian group. We also mentioned that in this construction, all these steps decays at a polynomial rate, although the actual rate are different, but they all decays at a polynomial rate like R to the negative alpha. And also know that the fundamental group of M is the same as this gamma. Sorry, I think I made another typo here. So here should be gamma, be a lattice. Yeah. So the fundamental group is not a virtually abelian here. It's a torsion-free Newportian group. And the next example is we can explicitly construct. Oh, by the way, in the Bernard-Bourdais example here, their warping function is not explicit. It satisfies certain differential equation. And but in Wei's example, you can write down what's this F and G. Sorry, yeah, this GR. You can write down what's this F, what's this GR. So the next example here is we can, here it's similar to Wei's example. We can explicitly write down what's this H and what's this F, and construct this example here. It's a double warp product with this sphere and this circle. But this H decays at a polynomial rate, so Ln to the negative alpha R. And this one also has positive Ricci curvature when P is sufficiently large for suitable functions F and H. However, one cannot use a similar idea as Wei's construction to construct one that is, I mean, you cannot do this for an, say, NR instead of a circle. It's possible to, say, this n, you do the similar thing, right? You start with a simply connected nilpotent group, you start with a lattice, then you can construct a family of matrix GR on this n so that it has almost non-negative Ricci curvature. But however, when you're doing this word product, this term actually becomes the dominating term inside your Ricci M, inside the term Ricci M, so that one cannot construct one with a fundamental group that is nilpotent, that is torsion-free nilpotent, but still with positive Ricci curvature, if you want to use this logarithm decay function. So based on these examples, we can ask a question. First of all, are there any deeper reasons explaining why we cannot use a logarithm decay function, h, to warp a nilpotent closed manifold n, other than just saying, okay, the calculation didn't work. There's a term that is much larger than the others. We cannot do that. Are there any deeper reasons behind that? Or more generally, you can ask for a warped product, as written before, is the decay rate of the warping function related to the structure of fundamental groups? Yeah. Okay, so to address these questions and also the one that I mentioned, I mean this one, can we improve this readout? And when things are fundamental group is virtually abelian. So to address these questions, we introduce a quantity called the escape rate. So for any element inside pi1 MP, we denote as representing geodesic loop. There's an actual S, shouldn't be here. And C gamma. So for simplicity, we're gonna write the norm of gamma as the length of this loop. So we're gonna introduce a quantity to measure how fast this representing geodesic loop may escape from any bounded boss as gamma exhausts all elements in the fundamental group. Because we have seen that these loops may escape from any bounded sets. So here we're gonna introduce a quantity to measure how fast they escape, right? So here is the formal definition. If you have an open manifold with an infinite fundamental group, then we define the so-called escape rate of MP, which is a scaling invariant. So here, this is a ratio. So on the top is DH. DH is the hot stop distance. So this is the hot stop distance between P and C gamma. So let's draw it. So let's say C gamma is here. So P is here. So DH basically is the size of C gamma, right? So that. Then over the norm of gamma, which is the length. So basically this says you take the size over the length, then that's it, right? Then we take all these gamma as their length to infinity. We take the limit super of this ratio. Then we just define this as the escape rate. So in short, is size over length, then you take all these gamma to infinity. Then that quantity you get eventually is the so-called escape rate. So we're gonna make some remarks on the escape rate. First of all, it's this quantity always between 0 and 1/2. This is because for any geodesic loop, its size is at most so that the sizes over length is always less than or equal to 1/2. Because it needs to come back to the base point eventually, right? Then secondly, if the escape rate is strictly less than 1/2, then the fundamental group is indeed finally generated. So this follows from a theorem by Sommerny, which says that if pi1 MP is not finitely generated, then one can find the generators, a sequence of generators, gamma 1 until gamma k, infinite many, inside pi 1 and p, such that the representing geodesic loops let's call it C1 until CK, are minimal up to halfway. So if this is a CK, so it's always minimal until it's halfway there, all right? So in other words, in this case, you have size over length is exactly 1/2. So in other words, if the fundamental group is not finally generated, then you can find a sequence of elements so that this ratio size over length equals to 1/2. So then because when we define the escape rate, that's a limit soup. So you get 1/2 exactly, all right? Okay. Next, if all the representing geodesic loops are contained in a bounded ball, so that is the analog we mentioned before. Then in this case, we have size over length, then size is always less than or equal to r, while our length goes to infinity. So this will give you EMT equals to 0, right? But EMP equals to 0 also includes more cases. For example, as long as these representing geodesic loop escapes from any bounded balls at a sublinear rate with respect to their length, then EMP also equals to 0. And the next, this one is not entirely trivial, but I'm just mentioning this result here. So 0 escape rate actually does not depend on your base point. If you have a manifold of non-negative Ricci curvature and this EMP equals to 0 for some P, then EMQ equals to 0 for all Q. So the next comment is about how escape rate is related to the warping functions if we consider a double warp product. So here we consider, and here we're warping a circle, but in general, you can warping other things. So we have seen the picture before that. Your manifold contains a portion looks like this. So this is not the entire manifold, but a portion of that. Say, let's say if we have a P here as our base point, then if I want to draw, so this is circle. So I just consider you go circle 1 round and go circle 2 rounds and K rounds. Then as this K increases, then how the representing geodesic loops look like? We ask this question. So I can draw one here, just goes K rounds, right? Instead of that, I can also take advantage of the thin end, because representing geodesic loop should have the minimal length, right? So if I just go K rounds here, it does not have minimal length, because if I take advantage of the thin end, this one actually has smaller length. But this also increased the size as well, because we go towards the end of this manifold. So, well, intuitively, if you have a picture like this, the representing geodesic loop, first of all, it will escape from any bounded balls, right? It'll use the thin end to shorten its length. And also, the faster this HR decays, then we'll take more advantage of this thin end. So the larger the escape rate will be. So that's roughly the intuition. So in fact, one can show that if HR, so that's the warping function, if HR decreases to a positive number, C positive, then the escape rate is 0. And if HR has polynomial decay, then the escape rate is positive. If it has logarithm decay, then the escape rate is 0 as well. So this logarithm decay is indeed the case that so they escape from bounded balls at a sublinear rate that we mentioned here. Okay. So now we're going to talk about the main theorems about in this talk. So the first theorem says if we consider M open manifold non-negative Ricci curvature, if the escape rate equals to 0, then it is virtually abelian. So this generalized the analog for closed manifold that we mentioned before. So if all the representing geodesic loops are contained in a bounded ball, then the fundamental group is virtually abelian. So here, it may contain a bounded ball, but it may also escapes at a sublinear rate, right? Then the fundamental group is virtually abelian. It also addressed the question that, where is that? Here, like is the decaying rate of the warping function related to the structure of fundamental group, or why we cannot use a logarithm decay warping functions to do a nilpotent closed one, to warp a nilpotent closed one. This is because if you have logarithm decay, then you should have 0 escape rate, right? While here by this theorem, 0 escape rate means the fundamental group is virtually abelian. So it will be impossible to warp a nilpotent one by using logarithm decaying functions, all right? So the next theorem is a further generalization of the above one. So it says that there is actually a universal gap on that. So given any dimension n, there is a positive constant epsilon n, such that for any open manifold of non-negative Ricci curvature, if the escape rate is sufficiently small, smaller than that universal constant, then pi 1m is virtually abelian. So this result will be on archive soon, soon-ish. So the contrapositive of the above theorem also gives a geometric characterization of any open manifold of non-negative Ricci curvature and a fundamental group that is not virtually abelian. So for example, if you have the fundamental group contains a torsion-free nilpotent subgroup of step at least 2. So step just means the nilpotency length. So in this case, it's not virtually abelian then by this theorem, we know that the escape rate must be strictly larger than the constant epsilon n. So when you're translating this back to the definition, that means we can find a sequence, gamma I, so that the size of C gamma I is at least epsilon n times the length of C gamma I, right? Okay, so now we're gonna move on to how the theorem is proved. So I'll talk about the 0 escape rate first, then I'll also give a little bit sketch on this escape rate gap. The gap thing is actually built upon the 0 escape rate case. So we're gonna study things from the infinity. So this is the so-called asymptotic cones. So for an open manifold or non-negative Ricci curvature, we can use the so-called pointed Gromoll-Hausdorff convergence. So for any sequence I to infinity, we can always pass to a subsequence. Then this I inverse MP, so this is you rescaling everything back, or you say blowing things down. Then that converges in the pointed Gromoll-Hausdorff topology to a pointed limit space, Z. And we call this Z an asymptotic cone of M. So the non-negative Ricci curvature condition says that this limit always exists up to a subsequence, right? But this limit may not be unique in general. If you have non-negative sectional curvature, then it is unique. For Ricci curvature, it may not be unique. And we can also apply the same asymptotic geometry, so this idea, to the universal covering, because we're starting the fundamental group, right? So for the universal covering, it has this gamma action. So here, gamma is the fundamental group at P. Then we can consider this so-called equivariant pointed Gromov-Hausdorff convergence. So here we take the gamma action into account, then that will also pass to a limit G action on the limit space Y. So this capital Y is an asymptotic cone of of M tilde, and Z is an asymptotic cone of M. So we call this YYG an equivariant asymptotic cone of M tilde gamma. Now, again, this may not be unique in general, right? Okay, so now we're gonna stray a little bit away from the Ricci curvature thing. So, but still related to asymptotic cones. So this part, at the end of the day, this part is not directly related to the thing in this talk, but actually it serves as an inspiration of the work here. So this theorem by Gromov, actually we mentioned it before. So if we have a finitely generated group of polynomial growths, then gamma is virtually nilpotent. So a key step in the Gromov's proof is considered the so-called asymptotic cone of this gamma endowed with the water metric. So this will converge in the pointed Gromov-Hausdorff topology to a locally compact homogeneous length metric space. Then later, Pensu showed that the asymptotic cone is indeed unique and give a detailed description of these asymptotic cones. They're indeed simply connected nilpotent Lie groups with left invariance of Finsler metric. But anyway, we're not gonna need these things here. Okay, so this may not be more related to the thing we have here. So if we have a closed manifold M, and we don't pose any curvature condition on M here, we can give a natural metric on the fundamental group by using the orbit on the universal cover. So we just say the distance between gamma 1 and gamma 2 is the distance between the orbit points gamma 1 p tilde and gamma 2 p tilde on the universal covering. Then this rho is indeed by Lipschitz equivalent to any word metric on gamma. And we can blow down the universal covering as well. This R inverse M tilde, sorry, this shouldn't be X, this is M tilde, sorry, P tilde. So this would converge as well, just as this I inverse gamma rho. Well, they're both pre-compact. And it converges in the pointed Gromov-Hausdorff topology to the same limit, which is a locally compact homogeneous length metric space, just as the case here. Then, okay, I think the interesting part is, even though this sequence does not have a uniform Ricci curvature lower bound, but this one still converges in the pointed Gromov-Hausdorff topology. Right. And another feature here is this gamma rho. So rho is the distance from the orbit. This gamma rho satisfies a condition so-called being asymptotically geodesic. So I'm gonna first read the definition and see what that means. So we say such a gamma rho is asymptotically geodesic if for any epsilon we can find S, which only depends on epsilon and gamma and rho, such that for any gamma, we can find a word, gamma j. So we write gamma as a product, as a word, product of gamma j, so that when you're adding all these generators, sorry, not generator, adding these words, when you're adding up these any of the lengths of these words is very close to that length of gamma. So let's say this is our m tilde. So this is the point p tilde, and this is the gamma dot p tilde. Then we can find these, say this is gamma 1, this is gamma 1 dot gamma 2, and this is gamma 1, gamma 2, gamma 3. Then you can, adding up the lengths in this Zizic way, this part plus this part, when you're adding all these things up, it's very close to rho e gamma. That is the distance between gamma tilde and gamma p tilde and p tilde. All right. So here, this S is indeed, S is roughly, say, epsilon inverse times the diameter of n. So if your gamma has length less than this, then you just choose the word as gamma itself. So then it's automatically true. So here we only want to apply this to gamma with large length, larger than this S. So you should think of this gamma p tilde as an orbit point that is very, very far away from p tilde. Then you can go back to p tilde in the Zizic way, so that when you're adding up these things up, it's very close to rho e gamma. So this is called asymptotically geodesic. So this condition assures that the limit, when you blow it down, this asymptotic cone is a length metric space if the limit exists. Like if you assume gamma has polynomial growth, then this limit will exist. Then this condition, well, the key here is this condition being asymptotic geodesic would imply the limit is geodesic. So that's why it has this name actually. Okay, so now we go back to, not yet, okay. But, well, actually go back to that. So if one just want to get the asymptotically cones are geodesic or are length metric spaces, we can actually weaken the condition a little bit. So this is the asymptotic geodesic condition. So we can weaken it a little bit to the following one, the so-called weakly asymptotically geodesic. So the only difference here is instead of S epsilon, we say S epsilon capital R, and we require this R over S epsilon R goes to infinity as R goes to infinity. Then we require the, so this estimate holds for gamma with length R. So in other words, if you have, so this is your gamma, let's just say on a group. So this is gamma, this is the identity. So I can go back to here so that each segment here is has length less than equal to S epsilon gamma, right? And this D, sorry, should be rho here. And here the distance between rho and the identity is R. So, and I require this R over S epsilon R goes to infinity as R goes to infinity. Previously, we don't have this condition because it just works for all R. It just works for all R. So as long as this ratio goes to infinity, then this actually guarantees that the limit is a length metric space if the limit exists in the first place, all right? Okay, so now we can go back to non-negative Ricci curvature. So we write this omega m tilde gamma as the set of all equivalent asymptotic cones of the universal covering with gamma action. And we mentioned that it may not be unique, so that's why we put a set here. So the key is to prove the following theorem, which says many statements are equivalent. The first says the escape rate is 0. secondly, the second condition says, the second statement says that the orbit is weakly asymptotically geodesic. So here is endowed with the metric rho. It just endowed metric from the orbit. So then the third statement says, well, this actually I mentioned. If you have weakly asymptotically geodesic, then here, if you consider the equivariant Gromoll positive convergence, that goes to YYG, then this orbit would converges to the limit orbit G dot Y inside the limit space capital Y. So the third condition says for any asymptotic cone, the orbit G dot Y, the limit orbit is geodesic in capital Y. Then the fourth condition says not only is geodesic, but it's indeed a metric product as RK cross a compact set Z. Then the last condition says the compact factor does not exist, right? So yeah, eventually you want to show this. So all of these are equivalent at the end of the day, but the most important one is you want to get this number fifths. So the orbit G dot Y is indeed isometric to a standard Euclidean space. So without this compact factor, it's not only geodesic, it's very rigid. It's just a standard Euclidean space. Okay, so here we give a sketch on how 3 implies 4 implies 5. I think I indicated why 2 implies 3. 1 implies 2 is fine. Yeah. So there are two tools we need here. The first one is the Cheeger-Gromoll splitting theorem, which generalized the Cheeger-Gromoll splitting theorem to singular Ricci limit spaces. So here, here singular Ricci limit spaces in our context, this just means the asymptotic cones. So if we have an asymptotic cone Y, capital Y, if this capital Y contains a line, then capital Y will split off this line isometrically. So the second ingredient is this lemma below. So geodesic sets in a metric product. So if you have a locally compact length metric space and a closed subset inside the metric product RK times Y. So let's say this is RK, then, and this is Y. So if you have this capital N as a geodesic subset, so inside the condition, a geodesic subset, inside this metric product that contains a slide. So let's say it contains this slice. Then it must be a product inside this RK times Y, right? So this is the entire RK times Y. Then N is indeed a subset Z here inside Y. So then it will be this product. Okay, you combine these two ingredients together and apply to the case here, then you can show that the limit orbit G dot Y is indeed a metric product RK cross some Z, and Z must be compact. If it's not compact, then you can split off a line again. So that's roughly the story. So this is basically the fourth statement here. So any asymptotic cone, then the orbit is a metric product RK cross Z compact. Then after this, the fourth statement implies the fifth one. So that's the technical part. Using a critical rescaling argument, then we can further get rid of the compact factor Z and show that all of these orbits are just RK without the compact factor Z. So I'm gonna skip this technical part. So once you get all of these limit orbits are just Euclidean space RK, then this indeed implies the virtual abelianness. So to explain this, we take a virtually nilpotent, sorry, not virtually new. So because gamma is virtually nilpotent, so we can take a nilpotent subgroup N of finite index inside gamma. So then we consider this asymptotic cone, equivariant asymptotic cone. And we know that this G dot Y is always on RK regardless which scaling sequence I inverse you apply. So this is the theorem we mentioned. So this is the fifth statement here. It's always a Euclidean space. Then because this N has finite index inside gamma, then you can show that this is also HY is this RK as well. Then with a little bit more work, you can show that H always acts on HY as translations. So here it just acts on the Euclidean space as pure translations. So one feature of the translation is if you translate once and twice is actually twice the distance, right? Well, what I mean here is if you have gamma is a translation, then the distance between gamma acting on 0, let's say gamma square acting on 0 is always twice the distance from gamma 0 to 0, right? Because it's just translation, it always moves forward. And when you go back to the manifold, so M tilde, this implies that for any element inside N with sufficiently large displacement at P, then it acts as an almost translation. In other words, here, gamma square P tilde, the distance between gamma square P tilde and P will be very close to twice of the distance between gamma P tilde and P tilde. So here is a 1.9, so it's very close. So this inequality holds for any gamma with large displacement, right? But on the other hand, one can show that a non-virtually abelian nilpotent group does not admit such a left invariant metric. So if you have a nilpotent group that does not contain an abelian subgroup of finite index, then it cannot admit a metric looks like this. So again, I'm gonna skip this part why this is not true. So that's yeah, I'm gonna skip this part for. But yeah, but that's roughly speaking. So the key is you show that for any element inside this nilpotent subgroup with large displacement, it acts as an almost translation. So gamma square is roughly at least 1.9 that length of gamma. Then that will imply the virtually abelianness, right? Okay, so that basically says explains why the zero escape rate case you have a virtually abelian fundamental group. So next, I'm gonna talk about the escape rate gap. That is, you have escape rate that is sufficiently small than some universal constant epsilon n. So here we're gonna give a sketch again. But to do so, let's first recall how we proved the zero escape rate case that we just explained. Roughly speaking, what we did is the following. We start with EMP equals to 0. Then we show that the limit orbit is always geodesic. Then we show that the limit orbit is always a matrix product RK cross some compact Z. Then we show that the limit product is always a standard Euclidean space. Then this implies virtually abelian. So to prove the escape rate gap case, we're gonna quantify this approach. for example, let's say the first step, right? We show that G dot Y is geodesic in capital Y. So here geodesic just means the eccentric metric and the intrinsic metric and the eccentric metric are the same, right? So let's say to quantify the first step above, we're gonna show that G dot Y, the limit orbit is very close to being geodesic. Well, being close to geodesic, there are many ways to write quantitative definitions. So we're gonna use the one here. We say that, so let capital X be a complete length metric space and N be a closed subset. And we fix a small number delta. We say that this N is delta geodesic if for any points AB, so for any points AB, we can find a chain of points in between, so that if you go along this chain, this is AK minus 1. If you go along this chain, then the distance is very close to the distance between A and B. And each adjacent point in this chain has distance at most delta dot DAB. So the definition is written in this way so that being delta geodesic is scaling invariant. So if you apply a scaling to that, delta geodesic is still delta geodesic, because inside definition, you always have this distance on both sides, right? So if a subset N is delta geodesic for any small delta, then it's just a geodesic, right? So as the quantification of the first step, so the first step means we want to quantify this being geodesic here. So the first step, we show that if the escape rate is less than or equal to some epsilon, then any limit geodesic is delta epsilon geodesic. And this number delta epsilon will goes to 0 as epsilon goes to 0, right? Okay. So then naturally we want to quantify the second step and the third step as well. So in the 0 escape rate case, next we showed that, so this is the second step. We show that the limit orbit is always a metric product as RK times Z, where Z is a compact thing. And then the third step, we just rule out that compact factor. So here we're gonna use a pointed Gromoll Hausdorff closeness to write the quantitative results. So with this in mind, one may expect we just say that the orbit G dot Y is very close to some RK cross Z, where Z is a compact thing. So here, how close it is, we want this to be controlled in a uniform way, only depending on epsilon and N. So this phi epsilon N goes to 0 as epsilon goes to 0. However, this has a clear abstraction because pointed Gromoll Hausdorff closeness cannot distinguish a non-compact space from a compact space with a very large diameter. For example, if you say two non-compact space, well, not necessarily non-compact, two space, they're close in the pointed Gromoll Hausdorff sense. That means if you take a very large ball around your reference point, then these two large balls are close. So if you have a very large circle, so a large circle, extremely large circle, and also a line, these two could be close in the pointed Gromoll Hausdorff topology. That's possible. If you want to distinguish a large circle and a line, then you have to say, okay, how close it is. It's like 1 over diameter. If they're that close, then I can distinguish them. They're different. But then that against this, we want to say that they're uniform close, right? Here we say phi epsilon N only depends on epsilon and N, while it does not depending on how large the diameter of Z here. Okay, so that's a clear obstruction you need to overcome if we pursue this approach. So to overcome this obstruction, the idea is the idea comes from something very simple. So it's this observation: for a compact space, say X, that is not a single point, then we can always rescale X by a number S, so that after scaling, the diameter equals to 1. So here clearly, I mean, S is the diameter of X, then taking inverse, right? 1 over the diameter. While for a non-compact space, regardless how you rescale it, which number you apply to it, a non-compact is still non-compact thing. So that's a that's a clear difference between compact space and non-compact space, right? It's a very simple idea, but this turns out to be the key, right? So then here is how to execute this idea. So for every asymptotic cone YYG, instead of considering this asymptotic cone alone, we'll consider a family of spaces. We'll consider SYYG. So that's all the scaling of this space. So every space, so every single one is an asymptotic cone, equivariant asymptotic cone at infinity, all right? So we'll consider this family together at once, all right? And we'll apply the Cheeger-Coding quantitative splitting theorem only when all these spaces in this family, they are almost splits, okay? So that's roughly the idea. So with this idea and many other work I may not want to mention here, so then we can prove this proposition. So if we have an open manifold of non-negative Ricci curvature and its escape rate is very small, less than or equal to some epsilon, then for any equivariant asymptotic cone, we can find an integer k so that for all s positive, this after scaling s capital YY, GY is close to a product. So here this GY, so this GY, this orbit is close to here RK times some ZS. And the distance between them can be uniformly controlled only depending on epsilon and n. So here, this capital X is a length metric space that may depending on S capital Y, and Z sub S is a closed geodesic subset of X, of XS. Moreover, one of them the following true: either this ZS is a single point for all S, or there is one so that its diameter is very close to 1. So this is close to the idea we mentioned here. If you have a compact space, then it's either a point. If it's not a point, then you can rescale it so the diameter becomes 1. So here, how we say that G dot Y is close to a product RK times a compassing in terms of pointed Gromoll positive closeness. We say that either this ZS is a single point for all S, or there is some so that its diameter is very close to 1, right? So with this, then again, you can, I would say similar, but not as similar because here the situation is much more complicated. And just as the zero escape rate case, we can apply a critical rescaling argument. Again, that's the technical part, but this is also the technical part, to rule out that compact factor ZS. In other words, well, once you rule out this compact factor, then you just say that this G dot Y is always close to RK, so RK, right? Then this scaling S really didn't matter anymore because all of these space will be close to RK. In other words, we proved the following: if you have a non-negative Ricci curvature, sufficiently small escape rate, then for any equivariant asymptotic cone, YYG, then YY gy will be phi epsilon n close to some arc cross x, and this orbit will correspondingly close to the arc slice inside this product, all right? Okay, once you have this, then it's close to RK, so some of the features still remains, like you can still show that if you have a nilpotent group N inside gamma of finite index, instead of saying that it acts as pure translation, it will be acting as almost translation on the orbit G dot Y. Then you go back to the manifold at large, you can show that any element inside capital N with large displacement also acts as translations, almost translations, in the sense that the length of gamma square is very close to that of gamma. Then this will implies the virtual abelianness. So that's roughly the sketch, all right? So that's all about the proof of the main theorems. So to conclude this talk, here are some open questions. So first of all, it's under some conditions, we can show that a certain class of manifolds actually has zero escape rate. So here, this result says if the universal covering satisfies certain geometric stability condition at infinity. For example, you assume that the universal covering has a unique asymptotic cone as a metric cone. Then this EMPL is always zero. So this is another long story if you want to explain why this is true, but here I'm just listing here without going into the details, all right? So then the conjecture here says this should be true if we just assume the universal covering has Euclidean volume growth. So under this Euclidean volume growth condition, the universal cover, well, any asymptotic cone of the universal cover will be a metric cone of hostile dimension n, but it may not be unique. So the thing is here is it may not be unique, then it have some issues rising up if we apply the strategy here. But we still want to say that this zero escape rate should be true. And if this conjecture is true, then as a corollary, for this class of manifolds, its fundamental group will be finite generated and virtually abelian. And moreover, indeed, you can one can bound the index of the abelian subgroup by some constant Cn air, by some universal constant Cn air. Here, air is the Euclidean volume growth rate. So here, air is the limit of volume BR P tilde over volume over the Euclidean volume. So the next question is, we have seen that we can use so this escape rate can detect whether the fundamental group is virtually abelian or not, right? So if the escape rate is sufficiently small, less than some universal constant epsilon n, then the fundamental group will be virtually abelian. So here we further ask a question whether we can find a series of constants so that escape rate can detect whether nilpotent groups, whether the fundamental groups are nilpotent groups of different steps. So more precisely, we ask whether there are positive constant epsilon nk that is strictly increasing in k, so that if the escape rate is less than this constant epsilon nk, then pi 1m contains a torsion-free nilpotent subgroup of nilpotency length at most k with finite index. All right. So frankly speaking, I'm not sure whether this is true or not. So this is just a question instead of a conjecture. Okay, so that's all about my talk today, and thanks for your attention.